Hello everyone and welcome to another video tutorial of the EMDLAB software. In this video, I am going to solve this magneto-static problem using the EMDLAB in MATLAB and also solve the similar problem in the ANSYS Maxwell software and finally compare the results. So, in the previous video, we wrote this code and we generated this geometry and this mesh. So, we used a detailed code to generate this geometry. We defined points and then segments, defined loops, faces, and finally we generated the mesh. But do we have to define points and segments like this? Yes, if you need to generate a detailed geometry and if you need to have full access to all segments and do all settings, yes. But you can generate this geometry in a simple way. Here, let me generate a new M file, okay, and save this M file untitled 1. When we define this geometry database, EMDLAB G to the database, we can define rectangle loop and also circle loop. Okay, so I can use this method. I need to have the loop tag. I write g dot add a rectangle loop. So we need to add this rectangle. This is the x axis, this is the y, and I am going to generate this square. The x and y coordinates of this corner point is x0 and y0. This is the width of the rectangle and this is the height. So I can define this rectangle loop using this function. So here I write 0 and 0, 1 and 1. So now I can define a face, right? So here I don't need to get the loop pointer, just I need to know its tag. Here I define g dot add a new face. This is a square, right? And this is the tag. So similar to this one, let me copy and paste these 3 lines. Show a sketch, generate mesh, and show mesh zones. So here we have this mesh and this geometry, right? So we define this rectangle loop and we define this face. How we can apply mesh size? So if I write this code, if I call this method set mesh max length, actually I can apply a maximum mesh size for all elements. So now if I run this code, as you can see, we have this fine mesh. And here I can define a new loop, add a circle loop. The center point is 0.5, 0.5. The radius is 0.2. So this is the second loop and L2 tag. So if I run the code, here you can see the geometry, and this is the mesh. Here I can reduce the mesh size also. Okay, so using these methods, we can generate the geometry in a faster way. So as you can see in few line of codes, we can generate this mesh, right, for the problems that we are going to analyze later. So here I have this example, the C-core example. You can see the geometry here. Let me explain the geometrical parameters. So let's copy and paste this image. We have these parameters. This is the width of the window. This is the height of the window. This is width of the core. And this is width of the yoke. This is width of the coil. Okay. This distance, I consider it as d0. And here we have the air gap, right? So this is the air gap length. Yes, we have these geometrical parameters. Let's create this geometry first and then apply the boundary conditions. Here I have this geometry in ANSYS Maxwell and this zero vector potential boundary condition. The rectangle 1 and 3, the material is M400. The copper materials, these two coil arms, I defined these excitations and this matrix. Okay, I want to calculate the flux linkage to this coil for a specific value of the current. Here the coil current is 1000. Okay, the number of turns is 1. Actually, we need to set the ampere turn. So here we have these geometrical parameters, and for these geometrical parameters, if I analyze the model, I can calculate the flux linkage. Also, let me plot the solution mesh. This is the solution mesh. Let me apply a fine mesh also to all of these objects. Length space 3 and analyze it again. So this is the initial mesh. Solve the problem. Here we know that we have, right, the air gap and the solution of the field in this region is important. So the value of the flux linkage is 9.5. Here I multiply it by 1000. So this is milliweber. Let me write, increase the font size of this result so you can check it better. So this is 9.54 milliweber, the amount of the flux linkage for this mesh. So how we can generate this geometry in MATLAB? Here I have these parameters, the width of the window, similar to this one, 50 millimeters, width of the core 10, width of the yoke 10, height of the window 50, air gap is 1, D0 is 2, width of the coil is 10. And this is the value of the current. So here, like before, I define this geometry database, EMDLAB G2D database, and I define this closed polyline loop. Okay, so this loop, I mean, for the core. Actually, to define a closed polyline, we need to have the x and y coordinates of these vertices, right, to define this closed polyline. So knowing these geometrical parameters, we can calculate the coordinates. So this is 0 and 0. The coordinate of this point is width of the core plus width of the window. Okay, the x coordinate and so on. Here I defined this closed polyline. So this is the core. Then I define this rectangle loop. Okay, the coil 1, the coil 2, the yoke, and finally the air, the enclosure. So here is the enclosure. You can see the properties of this rectangle, the same one that I defined it here. And I set the maximum mesh length, show the sketch, and generate the mesh. Okay, so if I place a breakpoint here and run the code, you can see the generated geometry. Okay, so you can see the points, the edges, loops, and the regions that we have. So when we generate the mesh, we can show the mesh zones. M dot show mesh zones. As you can see, we have these mesh zones. Then I set the color of each mesh zone, right? Set mesh zone color, the core, yoke, air, coil 1 and coil 2. This is RGB. Okay, so you can select the proper color and use these three numbers here. So I set the colors. I use this method to refine the mesh. This is a standard refinement of the mesh. I will explain this method later. Then I generate the global mesh because we have different regions and we should attach these mesh regions together, and then I can show the mesh zones. So if I place a breakpoint here and run the code, you can see this generated mesh. After generation of the mesh and having one standard refinement to have a fine mesh in these important regions. So the next step is adding materials to the mesh object. Okay, so M is a mesh object, EMDLAB 2D mesh, triangular mesh database. We need to define materials, so I add these materials from the folder that we have. Okay, here in C, EMDLAB Win64, you can see the materials, right? So we have a number of materials here. You can define, edit materials, change the HP curves, right? And so on. So here I add the air, this electric steel, and copper. So the next step is setting the materials. I set the material of the core and yoke. equal to this one, the material of the air, the material of the coil 1 and 2, the same as these materials that I used. Then when we generate the mesh and add and set the materials, we should select a proper solver. So this is the solver object. EMDLAB solvers, magnetic static. This is two-dimensional, and we use the triangular mesh elements. The degree of each element is 1, and this is an isotropic, homogeneous, nonlinear solver. So we discuss these solvers in the next videos in detail. But for this magnetostatic problem, we should use this solver. The input of this solver is the mesh database. Okay, so using this mesh database, we define this solver. When we define the solver, we can set the units. We know that the unit of the length is millimeter. The unit of the current density is ampere per millimeter square. The unit of the magnetic vector potential is ampere per meter. The depth of the problem is 1 meter, like this one in ANSYS Maxwell that we have. The depth of the problem is 1 meter. Then we need to define the winding. So here, if I plot the geometry, m.show geometry, we have two coil arms. This is one coil arm. The direction of the current is in to the paper, and this is out of the paper. So I define this winding 1. Then I add the coil 1 to the winding 1. The number of turns is 1. The direction of the current is negative. This is into the paper. And then the coil 2, number of turns is 1. The direction of the current is positive. Then we set the winding current. The value of the current is 1000 amps. Then we need to set the boundary condition and solve the problem. So here I define the zero vector potential boundary condition in ANSYS Maxwell, right? We set the value of the boundary condition, right? Here, the value of the magnetic vector potential is 0. Here, we use this method, get free boundary nodes. This is the global mesh, m.show mesh. We know that we have these boundary points. I can plot this one, m.show free boundary. Okay. And how I can get index of the boundary points of the mesh using this method, get free boundary nodes. So if I run this method, I have access to index of the boundary nodes. Yes, you have access to all mesh data. Here, if I plot this m.show mesh, and if I hold on this figure and I write index equal to m dot get free boundary node indices, then I can plot m dot nodes index and 1. Okay, we have access to mesh nodes, use a star. So if I run this plot function. Here, as you can see, we have access to all, yes, mesh, boundary mesh nodes. So let me increase the marker size to 3. So this is now better. Even we can use a higher number for better visualization, right? So you can see these boundary nodes. I want to set the value of the magnetic vector potential equal to 0 for these boundary nodes. So using this command, we can set the vector potential boundary condition. Then we run the solver s.solve, and after that we can plot the Bmag, the magnitude of the flux density, and flux lines. So this is the number of flux lines, and these are objects that we are going to plot the Bmag on them. So if I run the code, as you can see, this is the relative error of the solver. Here we consider this number for termination of the solver. You can see the solver properties here. S dot S, the properties, right? We have max iteration. If I open this file, we have these properties, the relative error, max iteration, and so on. So here is the result. The distribution of the flux lines and the amplitude of the flux density. Now let's calculate the flux linkage. Here, I can call this method s.eval winding flux linkage winding 1, multiply it by 1000 to have it in milliwebers. If I run this code, as you can see, the value is 9.3. So what is the number here? 9.5. So here we used first order triangular mesh elements. The ANSYS Maxwell uses second order mesh elements, a better approximation. So if I refine the mesh again, if I call this standard refinement more and calculate the flux linkage again here, as you can see, the value is 9.45. That is more close to this one, okay, when we refine the mesh. But the result is acceptable, okay? Now let's change the geometry and calculate new values and compare. If I select this rectangle and move it in the direction of the y-axis, -5, and repeat this simulation, I want to check the calculated value of the flux linkage for this new geometry. When we change the position of the armature, the value is 8.2. So in our case, if I set the value of the y shift equal to -5 and repeat the code, this is the new case. What is the value of the flux linkage? Is 8.12, right? You can compare it with this number. So you can reduce the value of the air gap equal to 0.5, and let's have this critical position -10. So we will have a high local saturation here. if I analyze this here, and in MATLAB, I write -10 and air gap equal to 0.5. I want to repeat the same calculation. Let me plot the value of the B here in Maxwell. As you can see, we have this local saturation here. The value of the flux linkage is 6.82. So if I run the MATLAB code, we have this local saturation here also, right in this figure. And what is the value of the flux linkage? Is equal to 6.59. Okay, so yes, you can repeat these examples and try this simulation in MATLAB and in ANSYS Maxwell. Compare the results and let's continue modeling of the new examples in the next videos. Thanks for watching.